All right, so this is those lights, though. Nice. All right, hold on. All right, we're good. All right, All right, so this talk is called OMG So Random XD. It's basically a discussion of randomness and things that aren't randomness, but that people refer to as randomness. So randomness and related concepts, basically. So why should you listen to me instead of, just some random person? Well, because I have a super sweet handle. I'm a crypto nerd. I'm a baron in the micronation of Sealand, should you respect its sovereignty, which you should. Imera Libertas. I'm the research director for the Austin office of NCC Group, and I'm also a senior security consultant. So I've been doing security-related stuff on the offensive side for a while now. So let's start by talking about what randomness is. So the Merriam-Webster definition is actually pretty enlightening. It's basically you have some system, some set, where there's a certain number of items, each which has its own probability of occurrence. And randomness is when those elements all occur with equal probability, so equal frequency. So if there's there's like this uniform distribution across all possible occurrences within some system. So this is in stark contrast to the hot topic random, which is really more accurately described as arbitrary, right? So let's talk about a concept called entropy. Entropy is the measure of how much information is actually conveyed by any given message. So you can think of this by looking at different expressions of the same information in different forms. So you have the number 10, for instance, and no matter how many exclamation points you add to it, or emoticons or whatever, it's still going to mean the same thing. If you express it as a word, it still conveys the same information. If you express it in hex, if you express it in base 64 or as an MD5 hash, you're still expressing the same information, just in different forms. So while the MD5 hash might be considerably longer and more random looking, it actually conveys the exact same number of bits of information. You're still just conveying the number 10. And so a lot of people will try to generate more unpredictable values by putting it through some sort of deterministic transformation like MD5 or SHA-1, and really it's no harder to guess once you actually know what the construction is. So anyway, that's we won't be getting too much into that. We're mostly going to be talking about the nature of randomness. So there's different degrees of random data, starting from not random at all to, barely changing to truly random. And I use air quotes there because we're not sure if that exists, but we'll get to that. So we start off with a beautiful XKCD comic, and it might cause a chuckle, but if you've been doing code review for long enough, you've actually seen something like this, which is sad. I have actually seen pretty much exactly this, except the number was different. It was like 14 or 41 or something like that, and it didn't have the hilarious comment. But this is about as non-random as you can get. But then you have incremental data. Just add some static value over and over again. And again, I don't want to spend too much time on this because this is kind of all obvious to this point. But then you have formulaic data, where it's entirely predictable if you know how to generate it, and the information is all something that's available to everybody. So MD5, the details of the MD5 algorithm are available to everybody. Timestamps, that's something that anybody should be able to generate, give or take a little bit of clock skew. And then you have something called pseudo-random, which is our first foray into what's actually approaching random in any meaningful way. So it's the sort of thing that appears random to a human being, but there are ways of inspecting this data, and in a lot of cases, pseudo-random number generation is very distinguishable from actual random data. So let's talk about this a little bit. Imagine that you have an RSA token or some Google Authenticator code, and you get these numbers out of it. Well, this is interesting. When I actually had somebody come to me and say, hey, I noticed that my Google Authenticator keeps giving me these like weird, definitely non-random numbers. We should look into this because there's definitely some problem here. Like, why would it give me the same 3 numbers repeated twice? But if you really think about it, how many 3-digit numbers are there? When you're talking about a decimal system, 1,000 different 3-digit numbers. And so your chances of getting a 6-digit number, if it's completely random, completely uniformly distributed, is actually 1,000 out of a million, right? Or basically 1 in 100. Am I getting that right? No, that's 1 in 1,000. My bad. Yeah, so 1 in 1,000, right? And if you think about, that's for any given 3-digit number. Considering that, there's a bunch of different, so it could be any 3-digit number. You add to that the fact that you could have that number once forward and then backwards. That's, another 1,000 out of a million, right? So you could have any number repeated 6 times. That's 10 out of a million, which admittedly is not much. But the point is that humans are very good at recognizing patterns, even when no real pattern is actually occurring, right? We can look at numbers and make meaning out of them when there is no meaning. So in the same way, humans can be very bad at recognizing patterns where computers might be very good at it. But there's a cool little hack that you can do which allows you to more readily see the randomness of numbers. And this is in graphing, right? We can take random numbers and graph them on a in a three-dimensional way, and all of a sudden, something really fucking cool happens. So let's see some pictures from a bit of research from this guy, Mikhail Zalewski, a brilliant guy, engineer at Google now, goes by El Camtuff if you're familiar with that handle. So a long time ago, he did this research on TCP sequence numbers. As it turns out, if you can predict TCP sequence numbers that will be generated by some host, you can pretend to be any IP you want connecting, and you can spoof some IP on a TCP connection, which, back in the day meant you could, abuse IP-based trusts, and to some degree you can still do that, but this is one of the more interesting looking ones. This is a graph of the TCP sequence numbers as would be generated by an unpatched Cisco iOS version 12.0. And you can see that there's this like three-dimensional, like it's on all the sort of axes, it's sort of, it's almost like there's this weird like alien cube that it's creating, right? There's an adherence to axes and a sort of echo that patterns out. And we can see something much more, that adheres much more closely to the axes, but, in sort of a planed way for HPUX version 11. And if we take a look at old versions of Windows, we can see Windows 98 has, had problems with the generation of random numbers for TCP sequence numbers. Again, adherence to axes and sort of like, this sort of like edge of a cube thing. And then we go to Windows NT and we see there's still very, very strong patterns, but in a much different way. Now, once we get to Windows 2000, we can see, it's much more evenly distributed amongst a cube, but you can see that around the edges it gets a little bit lighter, so it tends more towards like the middle there, so there is still a significant bias. Now, what's hard to see just by virtue of the fact that the audio visual or the visual setup, not the audio, that has nothing to do with it, obviously. The visual setup here is a little bit hard to see, but there's a little bit of just sort of dusting, like just powdered donut dust around this cube. So some of it lies outside this cube, but there's a whole range of values that aren't really getting hit here. So even this, though it's distributed pretty evenly among this cube, is still like limited to this area. So it's not perfect, but it's better than, well, this, right? So let's talk about some bad pseudo-random number generators. So this is one that actually sees a lot of use. It's called the linear congruential generator. So the LCG, or linear congruential generator, is a form of pseudo-random number generator that just uses a multiplier and an addend and a modulus to just cycle through numbers within a particular space. It's very, very simple. It's the sort of thing that, you know, given some like hand calculator that a bank gave you 10, 12 years ago, you could iterate through states. Now, the thing about linear congruential generators is that if I can get the internal state, I can then iterate forward and backward an arbitrary number of states. Now, the problem is that in some cases, in actually insanely common cases, the output of the linear congruential generator is the internal state. There is no difference between the internal and external state. So it iterates through the state with this simple operation and then just outputs wherever it's at. So anybody receiving one of a series of numbers from this can actually iterate backwards or forwards in state. So this is the exact operation that libc uses for its rand function. So it has some state. If you seed rand with srand, it just basically sets state to whatever you put into it, and then performs this operation on it to iterate forward in state, and then will just spit out state anytime you request another random number. So I've actually used this on a real-world engagement where somebody was using rand to generate passwords and then salts, and then, you know, hash a password with the provided salt. And so I could take the salt, get the internal state back from it, and then iterate backwards and figure out what the password that was generated before the salt was, just because of the weak nature of linear congruential generators. And it's, you know, completely, you know, unsuitable application to anything security related whatsoever. Now, another interesting point, java.util.random also uses a linear congruential generator. Again, don't use this for anything security related, but it's just a tiny bit better because it has a 48-bit state instead of a 32-bit state, and when it spits out a number, it only spits out the lower 32 bits. So you're missing 16 bits of information. Now, given a couple states, you can narrow it down and say, okay, only this state could have been the initial one, so you can recreate the internal state based on a series of outputs, but it's not quite like libc rand, where one state means you can recreate the entire, you know, one output means you can recreate the entire state. Now, you would hope that there's something better than this for, you know, security-related stuff, and there absolutely is. There's a number of different weak PRNGs, but let's talk about strong ones. So cryptographically strong pseudo-random number generators, another step up, right? Another step towards truly random. So these are actually used, cryptographically strong pseudo-random number generators are actually the basis for stream ciphers. So stream ciphers, you basically, who knows what the one-time pad is? Hey, great. So for those of you who don't, basically the algorithm works like this. You perform an XOR operation against your message with completely, truly random data in order to encrypt it or decrypt it, right? Because if you apply the same XOR operation with the same operand against anything twice, it goes back to its original state. So it basically does nothing. If you XOR anything with something else twice, it just doesn't do anything. So the idea is that you can not really say with any certainty that one key was used as opposed to another. And there's a key that will transform a message of a particular length into any other message. You could supposedly decrypt some ciphertext with the one-time pad into anything you wanted, and there's no statistical way to say that, okay, this ciphertext is most likely to be, whatever, unless you know the source of randomness is and you know that it's bad or that it repeats or something like that. So if you have a system whereby you can generate unpredictable numbers, and here's an important distinction, unpredictable versus random. Unpredictable, so a cryptographically strong pseudo-random number generator, you feed it a seed, which is like just some number that you make up. You get it from a true random source, and it acts as something like a key when you use this as a stream cipher. It's going to generate, no matter how many times you put the same seed in, it's going to generate exactly the same set of numbers as outputs. So that's not random at all. There's exactly one thing that can occur when you do it. It's totally deterministic. It's not random at all. However, it's unpredictable. And if you take 999 bits of this output from this pseudo-random number generator, provided it's cryptographically strong, you shouldn't be able to guess what that last bit is going to be, 1 or 0, with any better chance than just random guessing. And if you do, that's what's called a break, right? But that said, this kind of sounds like this is an attack that's like way, way advanced, and like no adversary is ever going to have this advantage. But in reality, when you're talking about stream ciphers, if you know the plain text for a certain amount of data, you can just XOR that with the encrypted version and get the key for that particular part of the message. And so if that part of the key relates to anything else, like maybe the key repeats every 10 bytes or every 50 bytes or something like that, you might be then able to decrypt other parts of the message that you didn't already know. So let's talk about how a cryptographically strong pseudo-random number generator might be constructed. I'm guessing everybody here is familiar with hash functions, and just sort of in general, not like how they work internally, but what a hash function is, what purpose it serves. So SHA-1, if you don't know, is a hash function. Otherwise, welcome to your first security conference. So imagine that you decide to use SHA-1 or some other hash function to generate pseudo-random data. So the way that you might construct this is to have one piece of data that doesn't change for all of your communications with a particular party, right? And then you have another piece of data that changes every single message. And then you have a third value, a counter, because at some point, one hash worth of data is not enough for a key. If you're trying to encrypt more data than that, might not be enough. So imagining that your key is my secret password and your nonce is Nancy McNonspace, you would hash, my secret password Nancy McNonspace 0, and then my secret password Nancy McNonspace 1 and 2 and 3 and so on and so forth, until you had enough hashes that you could take those series of hashes, use them as a key, and encrypt and decrypt your data. So you've just constructed a stream cipher out of SHA-1. Pretty cool. Now, the problem is that SHA-1 actually has some properties which make it unsuitable for this, and while Java used to offer SHA-1 PRNG, I don't think it does anymore. I think this is deprecated now because, as it turns out, SHA-1 has some biases in some number of the bits, so you're more likely to get particular hash outputs from SHA-1 than others. So this turns out to be unsuitable as a cryptographically secure pseudo-random number generator. But it at least comes close. You can see how this fulfills the requirements, right? So the thing is, when we talk about truly random data, computers have a really tough time with that. In fact, we've worked very, very hard to make sure that computers are very deterministic, that every time you do a particular thing with a computer, you get the same outputs. And that's a good thing, right? We want consistency out of our computers, right? Most of the time. Sometimes you want non-determinism. You want randomness. But computers they have that engineered out of them very, very, very strongly. So there's a great story out of Silence on the Wire, and I apologize to anyone who's already read this book, but I'm just going to quickly recount a story. Again, Mikhail Zalewski, brilliant guy. So basically, there's two randomness sources which are available via the file system on various Linux distributions, dev-random and dev-urandom. Now, dev-urandom is actually a cryptographically strong pseudo-random number generator, which is seeded with actual randomness. Now, dev-random is just a direct source of that true randomness. And that randomness is pulled from a variety of different sources, but a while ago, it was just based on like nanosecond level keystroke timings, or at least as low as the system could measure, right? Now, the thing about dev-random is that when you poll it, if it doesn't have anything in the entropy pool, it says, sorry, can't help you out. So it used to be possible to continually poll dev-random until you had exhausted all the entropy from dev-random. And so it started to block. And you knew that as soon as you polled it and it had more entropy for you, a user hit a keystroke. And so if you polled at a very fast rate, every 10 milliseconds or so, just as fast as you possibly can, you would get fairly accurate keystroke timings. Now, the funny thing about keystroke timings is that you can actually, with a reasonable degree of success, recreate what keystrokes were pressed based on the timing between them, because something like a double letter is going to occur very quickly, whereas typing two keys that require you to use the same finger is much slower. Typing two keys that require you to use different, fingers from different hands is going to be a lot faster than that, but not quite as fast as double letters. And so there's all sorts of statistical properties there that you can measure and get some decently accurate, 50 to 75%, I think the original paper on it was able to get. So pretty cool, right? They fixed that, so now there's like a buffer that fills up, and it's something like every 500 milliseconds. If there's more entropy available, it's dumped into the entropy pool and made available, plus there's more sources of entropy. But what kind of sources of entropy can a computer actually pull on? So these are things that are not random. We know that these happen in a way that is not uniformly distributed and so is not truly random. But electrical variations, small variations in voltage, mouse movements and the timing of those movements, keystroke timings at like a low level, and any combination of those, these are all things that are difficult to predict, difficult to model in any meaningful way, especially when you combine them. And then you have data which is about the closest that we consider to random. So really what this means is we have no idea how to model this. We don't know how this works from like a physics standpoint or from an electrical engineering standpoint. We can't say like why these events occur when they do or how they do, and so we just rely on that as a source of unpredictable data because it's sort of the Scrooge McDuck problem. Like you could have potentially figured out a way to model this, but you could probably be swimming in a swimming pool of money because you've made some, scientific breakthrough that nobody has made, and so why use it to, predict one of the sources of randomness from, a computer system. So radioactive decay, that's a big one. There's a lot of hardware modules that you can plug into your system which just have a little radioactive element inside them and basically a Geiger counter, which instead of like making a click sound will send a signal like, hey, got another decay event. And then those timings are used for entropy. The company Cloudflare actually has a wall of lava lamps, no joke, a wall of lava lamps that they train a webcam on. And between the sort of unpredictable, and this is kind of weird that lava lamps are sort of like something we find hard to model, or maybe it's just no one's, been patient enough to try to like figure out how a lava lamp could be modeled. But they just have a wall of lava lamps that they point a webcam at, and then they just take color data from that image and mix it all together, and it's something of an unpredictable state, especially with all those lava lamps in tandem, plus the optical noise from the webcam. So that's interesting. So this actually turns out to be a relatively good way to get random data. But the thing is, you know, as I said before, humans are very bad at seeing randomness. And we have all sorts of tests for randomness, but with a properly designed pseudo-random number generator, you can pass all the tests that we have for random data. So in truth, we don't really have any good way to say whether or not anything is truly random. It's reasonable to say that we live in a universe that is governed by the laws of physics, and we understand that those laws are deterministic. And then there's some, you know, theory that, you know, quantum events, the multiverse theory, that randomness comes from which particular variation of the universe we're in, which universe within the multiverse we're in. But that's a whole different discussion, and that gets into philosophy and even theology. So I'll leave you with the thought that perhaps there are no truly random events that occur at all. And also, I'd like to take questions at this time. I'd also like to advocate for the new NCC logo, which I have designed, which is very professional. I hired a graphic designer, same guy who worked on Ski Free, very smart guy. So at this time, I'd like to open up the floor for questions. Or heckling. If you want to heckle me, that's cool too. I'm a big AHA fan. What? Oh, it's... yeah, so .trust is a top-level domain that requires you to undergo a certain amount of security testing, and NCC started it. So we wanted to go with .secure, but I think Amazon actually bought that up right before we went and hit the button. So that was awkward, and we had to switch last minute to .trust. One-click checkout. Nice. Any other question? Oh, that got a raised hand. I'm sorry. Can you? The axes on that 3D graph. Where you were graphing numbers. What are they, or what do they represent? What number space is that? That's a good question. I think it's explained in the strange attractors in TCP sequence numbers paper by Mikhail Zalewski. So if you look up strange attractors in TCP sequence numbers, it's a great read, and there's lots more of those graphs, and he explains exactly what the axes are and how the random number generator output was turned into those graphs. In general, you take, you know, whatever the random number generator is, you take its, you know, max output and min output, and make those the limitations of the axes. And then oftentimes what will be done is you just take outputs in a set of threes and just take, you know, X, Y, Z, X, Y, Z, X, Y, Z, and plot each three-tuple of outputs as a particular point in a three-dimensional graph. Go ahead. Well, there's lots of statistical tests that you can run on a random number generator, pseudo-random number generators, to make sure everything's coming out all right. You know, you can do the sort of graphing method. I haven't gotten to assess a lot of, or really any. I haven't gotten to assess any hardware-based random number generation modules. So I don't really have a process for that. But I would, there's a standard battery of tests. I think actually there's a FIPS specification that defines a set of tests, you know, bit run tests and things like that. I'm a big fan of the Monte Carlo test, which is basically so Monte Carlo is a technique by which you do estimation based on random number generators. So one of the most common ones is to estimate the value of pi. So you can take you can do something like we were talking about, where you take every two numbers and use them as x-y coordinates on a two-dimensional graph, and then sort of draw a circle in the graph and say, what percentage of points are inside this circle, what percentage of points are outside this circle, and based on that, how can we derive the value of pi, right? There's a and so you can kind of like take this hard-coded value of pi and compare like your generated value, your estimated value, to the actual value. And if you have an even distribution across the graph, you should get a pretty accurate estimation of pi. That particular test is very sensitive to errors in random number generation, and I find that one pretty damn useful. There's a tool called ENT, E-N-T. You can find it at formulab.ch, formilab.ch. I'll say that again so you can write it down if you wish. FOUR, like the number 4, MI, like the abbreviation for miles, lab, lab.ch, as in, I think it's Switzerland? Yeah, hey, cool, I got it right. According to this guy, anyway. Yeah, there you go. So there's a tool called ENT, which runs a standard battery of statistical tests to check for quality of random number generator outputs. I would say those tests are what I would run. I also have built and I maintain a tool called Feather Duster, which has an analysis engine for various samples. It's meant for encrypted data, but it runs many of the same tests that ENT does. And given a large set of outputs from a random number generator that I would be evaluating for quality, I would expect to see it pass all of those tests if it's a solid random number generator. You're welcome. Anybody else? Okay. Well, if you decide you have questions later, that's my email address, that's my Twitter handle, and you can just come find me and, we'll chat. Or was that a question back there? No. Okay. All right. Thank you very much.